So, hello everyone. This is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm going to deal with the course Computational Aerodynamics. The topic that we are seeing is substantial derivative and continuity equation. So, before that, let's revise the fluid dynamics, what we have discussed. So, basically, we had seen that CFD is an inventory approach where we can overcome the disadvantages of theoretical and experimental techniques, and this is the process of CFD which we have seen, and these are the governing equations which are solved in the CFD. So first one is continuity equation, second one is momentum equation, and the third one is energy equation. So here we have external flow and internal flow example. So there are two approaches in the fluid flow problem. So one is Eulerian approach and the Lagrangian approach. So while we are deriving the continuity equation for today's module, so we will be using the Eulerian approach. So as I told you, for the Eulerian approach, so we are taking the average quantity of the variables with respect to space. So if we are taking the average quantity, so pressure, velocity, and temperature, so we are discussing at the average section. So we are discussing about the grid, so structured grid, and this is a zoomed view of the structured grid. So as I told you, so grid is an entity where we will divide the domain into subdomains and we will simulate flow here. So we have non-uniform grid and uniform grid. So non-uniform grid in the sense the spacing between 2 points will vary. So here you can see that here you have grid point 1, 2, 3, 4. So here it is delta x1, delta x2 and delta x3. So delta x is nothing but distance between two grid points. So here you have two grid points. This is delta x1, delta x2 and delta x3. If these are same, let's say delta x1 is equal to delta x2 is equal to delta x3. So then the corresponding mesh is called uniform mesh along x-axis. So similarly, if you see this one, delta y1, delta y2 and delta y3. So the delta y1 is equal to delta y2 is equal to delta y3. Then it is called uniform mesh along y-axis. So the delta x1 is equal to delta y1 is equal to delta x2 is equal to delta y2, so on. If you have this condition, then this is called uniform mesh or uniform grid along both x and y axis. So this is what have been discussed. So here this is the non-uniform mesh along x axis. Here you can see the non-uniform mesh along y axis, and this is the non-uniform mesh both along x and y axis. So as I discussed, the difference between coarse and finer grid. So the coarse is nothing but less number of grid points, and the finer grid is nothing but so here you have more number of grid points. The solution obtained. So the solution obtained here will be if it is same for coarse and finer, then we can use the coarse grid. But if the solution changes as you're changing the number of grid points, so you should use more finer grid. So the unstructured grid. So basically for the structured grid, we are seeing a square or rectangular, or it's like a quadrilateral cell we have. But here for unstructured grid, you have triangular cells actually. So this is the difference between the structured and unstructured grid. And one more thing. So here we have the connectivity of grid points. If you take one grid point, so it will be connected to so many number of neighboring grid points. So whereas if you take a grid point in the unstructured grid, so it may be connected to 4. So let's say you have a structured grid here. So let's say this is the point. So it is connected with this one. So with 4 neighboring points. So if you take unstructured mesh here, so this will be connected to So let's say if you see this zoomed area, it is connected to 1, 2, 3, so on 6 grid points. Okay. So this is the difference between the structured grid and unstructured grid. And one more thing, for unstructured grid, the computation time will be very high. Why? Because when we take the grid point here, so we are solving the governing equations, continuity equation, momentum equation, and energy equation, these grid points. So when we are solving three equations at the grid points, so let's say you have three variables. So u1, v1, p1, let's say, at this grid point. Similarly, here you have u2, v2, p2. So if you have 10,000 grid points, then you will have u 10,000, v 10,000, and p 10,000. So at a particular grid point, you should solve three equations. If you have 10,000 grid points, so 3 into, let's say, 10,000. So nearly 30,000 equations you need to solve if you have a mesh size of 10,000. So if you compare the unstructured and structured mesh, so basically the size of the elements or size of the grid points or number of elements or grid points will be very higher actually compared to structured mesh. So and we had seen the applications of coarse and finer mesh. So near to the wall we will use finer mesh because we need to capture the boundary layer. So outside the boundary layer, so we assume that flow is inviscid. So therefore we can go for coarse mesh. Okay. So near to the wall regions and or the regions where we need to find our flow phenomena. So at that region we will use very fine mesh. So here we will discuss what is substantial derivative. So before that, here you can see basically it is a 3D space. So you have x-axis, you have y-axis, and you have z-axis. So if you want to define 3D space, then you need to define with respect to coordinate axis. So this is a Cartesian coordinate system. So basically x, y, z coordinate axis is called Cartesian coordinate system. If you have r, theta, and z, so basically this is called cylindrical coordinate system. So this is called Cartesian and this is cylindrical. Then you have r, theta, and phi. So basically this is called spherical coordinate system. So depending upon the geometry that we have, we will take the coordinate system. So here we have taken the fluid element as a cube or cuboid, let's say. So if you take a cubical section, let's say this is our fluid element. So if you want to measure the dimensions of fluid element, so since it is a regular dimension, so we can take as Cartesian x and y and z. So that is why, so we have taken Cartesian coordinate system to derive the substantial derivative. Okay. So here let's see how we derive substantial derivative using this diagram. So this diagram says that a fluid element is at some position 1 at time t is equal to t1. Okay. And after time t is equal to t2, the fluid element is traveling from one place to other place. Okay. So the dotted lines, whatever we are seeing, is a path followed by the fluid particle. So let's take this is a flow actually. So in the flow you have different number of fluid particles. Okay. So the fluid particles are not restricted to have certain path. So depending upon its momentum and depending upon the pressure gradient and external forces acting on the fluid particle, so the motion will be described. Okay. So when this fluid particle is going from one place to other place or one point to other point, how the fluid properties are varying with respect to space and time is mandatory. So what are the fluid properties we have? So we have pressure, so we have density, so we have u velocity, we have v velocity, we have w velocity. Okay. Or you can take it as then you have temperature. So you have these many aspects. So if actually the meaning of substantial derivative is the verification or is equal to the time rate of change. So the local derivative and the convective derivative. Substantial derivative will give the information about the fluid particle. So with respect to time, so at a particular point, so what is its acceleration, and with respect to like time is about the local derivative, and with respect to space when it is moving, so what is the acceleration? It's called convective acceleration. So we'll see how those terms are obtained. Okay, so here if you see the at point 1, so the fluid particle is here, at point 2 this is here. So when it is moving from one point to other point, so there may be changes in pressure, changes in density, changes in velocity, u velocity, v velocity, w velocity, and temperature. So how it is changing with respect to time and how it is changing with respect to space, we will see in the substantial derivative. Okay, so let's take, if you take any flow variable, let's take density. So it is function of x, y, x comma y comma z comma time. So let's say it is x1, y1, z1, and t1. So this is at initial point, let's say. So density at the second point is function of, let's say, x2, y2, z2, and t2, let's say. So x, y, z are called spatial derivatives, and t1 is nothing but it's a temporal derivative. So the fluid variable will depend on the spatial derivative, spatial terms, and the temporal terms. Okay. So now let's see how to obtain so rho 2 with respect to rho 1. So basically the density value at the second point is calculated based on the value of density at the first point. Okay, so why? Because this value of the density at the next step is based on the initial step, which is nothing but initial condition. Okay, so if you see, basically the value of density at the second point, so we can actually use mathematics where the Taylor series of expansion is used. So density at second point will be equal to, so density at first point plus the Taylor series of expansion which we have. So dou rho v1 by dou x into x2 minus x1 plus dou rho v1 by dou y into y2 minus y1 plus dou rho 1 by z is equal to z2 minus z1 plus dou rho 1 by dou t is equal to t2 minus t1 plus higher order terms. So basically the density at the next point or the second point will be majorly depending upon the initial density value and the derivative terms. Okay, so you have let's say it is dou rho by dou x. Here this is called delta x, this is delta y, this is delta z, and this is delta t, let's say. Okay, so this is what we have using Taylor series of expansion. So basically Taylor series of expansion is formalized like f of x plus delta x. If you take, that is like f of x plus dou f by dou x into delta x plus dou square f by dou x into delta x square by 2 factorial plus so on. So this is what we have. So this concept we are applying for our evaluation of value of density at the next point. Okay, so here you can see the value of density at the next point is written as rho 1 and the derivatives, spatial derivatives and the time derivatives. Okay, so this is what we have. So let's see how we will change this to our substantial derivative. Okay, so what we do is like we have this as rho 2 is equal to rho 1 plus dou p, let's say x2 minus x1 plus into y2 minus y1 plus dou rho by dou z into z2 minus z1 plus dou rho by dou t into t2 minus t1. So these are plus higher order terms. Higher order terms in the second derivative term. So this equation we will change it as so rho 2 minus rho 1 and divide this equation by t2 minus t1 everywhere. Okay. So what happens? So this would be t2 minus t1 is equal to so dou rho 1 by dou x into x2 minus x1 divided by t2 minus t1. So this is what we have plus dou rho 1 by dou y into y2 minus y1 divided by t2 minus t1 plus dou rho 1 by dou z here z2 minus z1 divided by t2 minus t1. So here you can see the third term. So x, y and z term. So these are your spatial derivative terms. Other one time derivative term. So dou rho by dou t into t2 minus t1 divided by t2 minus t1. So then what we have? So these terms are getting cancelled. So you have temporal derivative as dou rho by dou t. Here you can see dou rho 1 by x dou x and x2 minus x1 divided by t2 minus t1. So if like if you take the average quantity here, so this would change average derivative, then it will change to capital d rho by dt. Here you can see so x2 minus x1 divided by t2 minus t1. So then this quantity will change as u velocity. So this quantity will change as v velocity and this quantity will change as w velocity. Okay. So this equation we can this equation we can write in this way. So how we can write? So it is as d rho by dt is equal to, so basically this left hand side term is called the total derivative or material derivative or substantial derivative is equal to so u into dou rho by dou x, so v into dou rho by dou y plus w into dou rho by dou z plus what we have time derivative term dou rho by dou t. So basically this is called the convective derivative term. Okay. So this expression is called the convective derivative term and this expression is called the local derivative. Okay. So we will actually change this in a vector notation, but here you can see that we are written in the scalar form, in expanded form. So these expressions actually here you have two terms actually. So let's say this is first and second. So here this first term will discuss about the local acceleration. The meaning is it's convertive acceleration. So the meaning is like when the fluid particle is moving from 1 to 2 because of motion of the fluid particle with respect to space. So what is the acceleration associated with that? Information will be given using the first term, and the second term will discuss about so at a particular point. So what is the acceleration at a particular point and a particular time instant? So what is the velocity? Okay. So this dou rho by dou t, let's say. So this term actually you can see that it's a material derivative of the density. So instead of density you can use temperature, you can use velocity, so you can use any other term which we have. Okay. So finally what expression we have obtained? So we have d by dt is equal to, so let's say we have dou by dou t term plus u into dou by dou x term plus v into dou by dou y term plus w into dou by dou z term. So this is the time derivative term. So here you can see these are the spatial derivative terms. Okay, so already it is written velocity is equal to u of I cap plus v of j cap plus w of k cap. So we have a del operator which is equal to dou by dou x of I cap plus dou by dou y of j cap plus dou by dou z of k cap. Okay, so what is this one? So you can read it as a v dot delta. Okay, so dot product of velocity and and gradient. Okay, so you can see that's why you had obtained. So when you do dot product of these two things, so we get this expression here. Okay, so this material derivative or the substantial derivative terms are written in form of the local acceleration terms and the convective acceleration term. So here this thing you can see it is applicable for any parameter. So previously we had seen for density, so now we can write it for temperature. So how? So that would be d by dt is equal to dou by dou t of temperature plus u into dou by dou t of x plus v into dou by dou t of y plus w into dou by dou t of z. So this is what we have. So the substantial derivative or the material derivative, the total derivative will give the information of the local derivative term and the convective derivative terms of the corresponding variables. Okay. So with this, why we were using this, because so in the momentum equation, let's say you have F is equal to ma. Example. So what is m? Mass, which is equal to density into volume. A is nothing but the acceleration, which is dv by dt. So we can write it as a material derivative dv by dt. So this term, this acceleration term, can be written in this form. Okay. So we need to know what detailed information about the acceleration of the fluid particle. Fine. So with this knowledge, like we will go for the derivation of the continuity, momentum, and energy equation. So we had seen there are different approaches of the fluid element to derive the governing equations. So you can see there are 4 ways. Actually, we can split in 2 ways. So one is like control volume approach, other one is the fluid element approach. So here you can see basically this is fixed in space and this is moving in space. So the only difference what we have is here the control volume, as it is fixed in space, so the flow will enter and leave. So here the control volume is moving with the space. So the meaning is like the control volume will have velocity equivalent to the fluid. So the derivation, so when we derive the equations for the control volume in the fixed space and the control volume moving in the space, so there are difference. So here you will derive the conservative form of governing equations. Here you derive the non-conservative form of governing equations. So conservative form and the non-conservative form of governing equations. Okay. So when the equations derived for a control volume which is fixed in space, then you will get a conservative form of governing equations. And when we derive equations for control volume which is moving with the space, then you will get non-conservative form of governing equations. So this is one way of approach. And here you will be getting the integral form of equations. So the integral equations. Okay, why? Because we need to integrate for the entire control volume. So, and the approach B, so what we have is like a fluid element approach. So in the fluid element approach, so we will discuss about the molecules which are present in the fluid. So, and here it is fixed in space. So in this is conservative form of equation, and here it is moving with space. It is called non-conservative form of equations. So the difference here between the control volume approach and fluid element approach, what we have is, so we will derive the differential form of equations directly here. Or let's say do. Okay, here we will derive the integral form of equations. So this is the difference we have. But here you can see whatever the cases, if the control volume or the fluid element is fixed in space, we will derive the conservative form. If the control volume or the fluid element is moving with the space, then we will derive non-conservative form of governing equations. So let's see basically how we derive the continuity equation for a control volume fixed in space. So here you have basically we are deriving the continuity equation in a conservative form. So let's take the control volume. Basically control volume is an entity where we will see the effects of the fluid which is entering and leaving, and how it is affecting the fluid motion and how it is affecting the control volume. So the space which it has it entered. Okay, so now if you take the control volume, it can be of any shape. There is no fixed shape of the control volume. It can be any arbitrary shape. So that's why an arbitrary shape is dot. If you take a particular element in the control volume, so you have the element surface as ds and the elemental volume as dv. So what we are taking is like we will take the small elemental area. Likewise, we will take a small elemental volume, and we will apply our conservative, like our equations to derive. Okay, so our concepts to derive the continuity equation. So here you can see the fluid, the amount of fluid which is decreased in the control volume will be equal to the fluid which is leaving the control volume. So let's say if you have x liters in the control volume, let's say. Okay, so initially x liters. So basically whatever amount of x, whatever amount of, let's say it has gone y amount of liters, it has left. Okay, so basically the whatever the rate of decrease amount of fluid which is inside the control volume will be equal to whatever the increase or whatever the flow that is leaving the volume. Okay, so this is the basic principle what we have to derive our equation. So what we do is like we will take a small elemental area and we will let's derive. So the rate of decrease of mass inside the control volume, let's write in a mathematical form. So basically let's write decrease. So the decrease is shown as a negative symbol. So the rate can be written as dou by dou t. Okay. So this is this one. So if you want to see for the entire control volume, what we will do, we will take the integral form, amount of the rate of decrease. So this is what we have, mass inside the control volume. So this is total. So mass is nothing but density into volume. So what volume we are taking? We are taking as dV. Okay. So we are taking it as dV. So which is nothing but the elemental volume we have. So dou by dou t will be rate and rho into dV is nothing but the mass. So the integration what we have is like we are taking for the entire control volume. So the meaning of this term is the rate of mass decrement inside the control volume. Okay. So here this is mass, which is nothing but density into volume. So since if we are taking only these two terms, it is for only one elemental volume which is inside the control volume. If you integrate like a triple integral in the sense x, y, z, okay, if you integrate fully, then you will apply it for entire control volume. And dou by dou t is nothing but the rate, and negative is nothing but decrease. Okay, will be equal to what? The flow which is leaving the control surface. Okay, so that is what we have. So whatever the flow that is leaving the control surface is written in this form. So surface integral rho v dot ds. Okay, this is area vector and velocity vector. Okay, so this is what we have. So basically we whatever the words we had seen, we are written in a mathematical form. So final equation what we have is like dou rho by dou t integral plus so this is the integral form of governing equation. So the first term what we have is like the amount of decrement. So the here you have the amount of decrement of mass inside the control volume will be equal to the flow which is leaving the control volume through the control surface. So that's why we have taken so the flow rate which is leaving so through the control surface, particular control surface. So basically it is like rho AV m dot, we can take it as a rho AV term. So rho is nothing but rho here, area is nothing but ds, so velocity is nothing but velocity here. So this is a concept which we have. Fine. So here we can change from integral to what is a differential form. So first let us write the total uh, equations in integral for triple derivative. So we have triple integral of the first term which is dou rho by dou t into rho dv. But second term, like you have this equation, so which is rho v dot ds is equal to 0. So this term has to be changed to what is a triple integral. So this is surface integral to volume integral. So Stokes theorem has given like small formulation to change from surface integral to the volume integral. So this is what we have. So is equal to triple integral. So this is S, this is volume, this is S. So volume of del dot rho v into dv. Okay, so this is what we have. So this formulation will apply here, and the corresponding equation what we have is like plus. So what do we have here? Here also we have volume integral. So basically this is the total volume integral of the continuity equation which we have. So we can change this one too. So this is written in integral form. So we can write this one in differential form also. So if you take the volume integral and change it common, and like we can change from this one form to other form. Okay. So the corresponding equation what we will get is like dou by dou t into density, okay, plus del dot rho v is equal to 0. So this is the differential form of the continuity equation. Okay, so here you can see, so basically it is written in form of vector notation. So if you expand this one, so dou by dou t of rho plus del, so you have del. What is del? Del is nothing but dou by dou x of I cap plus dou by dou y of j cap plus dou by dou z of k cap. Okay, so you know the velocity vector is equal to u of I cap plus v of j cap plus w of k cap. So this is what we have. So we can substitute these two things for a dot product, and what we get is so dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w is equal to 0. So this is what we have, an expanded form of continuity equation, so which is unsteady. So the continuity equation will give the information whether the flow is incompressible or compressible. That's it. So based on the density. So if the flow is incompressible, so this term will go off, and the values of density will, since it is incompressible, it is constant. So rho So rho will come out and it will get divided by 0, or 0 divided by rho it is. So dou x by u plus dou by dou y of v plus dou by dou z of w, so which is equal to 0. So when you take only steady continuity equation with compressible, then you have these terms. So when you take incompressible equations, then you have the dou by dou x of u plus dou v by dou z, dou v by dou y plus dou w by dou z is equal to 0. Okay, so this thing is nothing but del dot v is equal to 0, which is written in vectorial form. Okay, so here the continuity equation that we derived in a conservative form of equation, and we had changed initially from what do you say, initially surface integral to volume integral. Then we had taken the volume integral common and we had obtained the differential form of governing equation, which is continuity equation. So the continuity equation will give you the information about the flow, actually how it is moving with respect to density, whether it is a compressible or incompressible flow. That's it. So we don't have any information whether we have uh, any like viscosity or non-viscous or any inviscid effects using this equation. So this equation will just give you the information about the flow, whether it is compressible or incompressible equation. Okay, so here you can see, so basically in this equation you have 4 variables. So how many? Like you have the density, you have u velocity, v velocity, w velocity. Okay, so depending on the assumptions, your variable count will decrease. So let's say if it is incompressible, the density will go off. If it is 2D, then your w will go off. So the remaining thing what we have is like dou u by dou x plus dou v by dou y is equal to 0. Okay, so this is the 2D continuity equation, so which we have. Fine. So in the next module, let's see basically what is non-conservative form is like you have the movement of control volume with respect to the flow. So we need to take the relative velocity, and next we will see in the fluid element approach, so how the differential form of the continuity equation is derived. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.